made up. Test 3 is about, half as hard or so. I mean, it'll be, but again, I don't want to say that. I mean, I gave it the, I gave it the idiot test this morning at breakfast. I took it after I hadn't seen it for a while, kind of scrambled the questions, took it, and it took me about 10 minutes to do. Okay? So, you should be able to get it done in 50 minutes to an hour without much trouble. All right? What's that? I got them all right. Yeah, what's that? Oh, no, I haven't given it, but I took her advice on what to do. In other words, don't assign the same type of problem 4 times. Just let it go. Let the wires and currents go. All right? Just let it go. All right. Anyway, so let's talk about. First of all, I think what we'll do is I've got the slides called up here for mirrors and the and lenses. Yeah, let's go through the slides. It'll take us about 10 minutes. I'm kind of just going to go, here you go, here you go, here you go. Then we'll do 2 examples. Then I'll tell you what's going to be on the exam, and we'll call it a day. And then Friday, I should have them graded because I'm not going to kill myself and try and grade 16 problems this time. I'm grading 6. You have 6 problems, all right? Oh, and the other thing I needed to mention too was I've gotten a smattering of emails from some of you going, I haven't missed the class yet. Why do I not have a score for quiz 7? Because you didn't take it yet, all right? You finally took it, and I gave it to my boy Zhang. I didn't know how many quizzes you all had done, and so when I put your 10 points for showing up to collect your quiz that one day all on quiz 8, because I didn't know how many quizzes you guys had taken, so that's why there was a blank in 7. It's filled in now. Yes?
So our test quiz is on Wednesday?
Yeah. Yeah.
Okay.
Yeah. Always has been.
I just thought it was going to be like one big problem.
Oh, no. It's going to be 6 little problems over the, like, 5 or 6 big ideas from the thing, okay? Be a piece of cake. All right, so that I needed to clear that up. And same thing with your homework grades. I won't say who the scoundrel was who came into me and said, you know, that one homework problem assignment was only worth 13 points. You've got 70 for it in Blackboard. Went, oops, forgot to change that from last semester. So I went back and changed it to 13. So that lowered some of you had like 60 extra credit points. Not anymore. Those are gone now. Okay. All right. But I would have caught that eventually anyway. Probably. Yes?
What about our quiz extra credit?
It's on quiz 8. That was your quiz 8 for picking up the test?
No, showing up that Friday.
Showing up that Friday? Oh, that was already put on your test score. What? No. You got the 10 for, except I stopped at Shane. All right, but then I gave the rest of you. If your name was S, started with Soltz and lower, I forgot to add your 10. They've been added for attending the thing. Yes, they have.
No, not that at all.
What now?
The Mastering Physics quiz.
Oh, the 20 on that. Oh, I'm sorry. Yeah, I haven't included that yet. Yeah, because there's, yeah, no. Oh, I'm sorry. Yeah, okay. Yes.
What about the 10 points for coming to Saturday?
The Weeblos on Wheels. I got the roster from David. I'll have to get that from him. But I will. All right. Now, let's go ahead and see, that's one reason why I wanted to get out of the extra credit business, but I couldn't help myself. I just dipped my, put my tongue on that frozen flagpole one more time. All right. Anyway. Okay. Let's take a look at the thing here. And let's just go to the view, the show. And from this current slide. All right. Here's what we're going to be looking at, mirrors and lenses. We already talked about these. All right. Here's a concave lens. Okay. Concave lens. You've seen concave lenses. Here we go. Here's a good thing to know about concave lenses. All right. Now look. Here's one. Now notice where we put the object. The object we put. One thing you can do with a concave lens, if you've ever wanted, Have you ever been bored, like at grandma's house at Thanksgiving dinner, and the adults haven't excused you yet to go, and so you're sitting there playing with the spoon, looking at your reflection? That's a concave mirror, basically. And did you notice that your reflection would be upright until you got real close, and then turn upside down, and then kind of disappear even? Well, that's what's going on here. All right. So anyway, C is your curvature. All right, how do we get the focal length if we're given the curvature? What is it? F is what? The curvature divided by 2, right? So it's the radius of curvature. Here's your radius of curvature, and here's your focal length, all right? And just write this down, and don't ever forget it, all right? Just write this down right now, real quick. Here is, if you want to ace 3 questions on your test, know this and all the implications. Now, you just can't know this, but you got to know how to use it and how to work it. But here you go. 1 over the focal length equals 1 over the distance of the object plus 1 over distance of the image. Okay? There you go. Magnification equals the height of the image divided by the height of the object. Well, that makes sense to us. Height of the image divided by height of the object. And it also equals, we could do a bunch of algebra that would bore you to death and not get us anywhere, or I can just write it up here. It's also equal to this, the negative of di over do. Okay? There you go. For chapters 20, this one, for chapter 23, this is your bread and butter. It's all you need to know. One last thing you need to know for lenses. Okay, how many future optometrists do I have here? Any future optometrists? None? Really? It looks like a good, because people are always going to need glasses, and it's not gooey. I think optometry would be cool to go into. Anyway, I guess it's kind of, you got to still look in people's eyeballs and stuff. And anyway, all right, so where was I? Oh, yeah, power. If you want to know the power of a lens, here's your key equation right here. Power of the lens is equal to 1 over the focal length in meters. So if you're asked what is the power of this lens, you'll go, oh, I found my focal length, flip that sucker over, and then convert it to meters. And any of you know what your eyeglass prescriptions are written in? Diopters is what that's called. So you'll see a D for this. D for diopters. All right. Quick and dirty, there is chapter 23 in a nutshell. Now, I'll show you some of the cool things from the slide that you just, I don't know if they're cool or not, but just things you need to kind of know. All right, now, with a concave mirror, here's a concave mirror. Now notice, if we put the object between the radius of curvature and the focal length, the object is going to turn out to be real, inverted, and enlarged. Inverted means when your magnification comes out to be negative. Okay, first of all, quick question. I know some of y'all can't see over there when I do this, but sorry. Quick question. Let's say you get a magnification and it equals -3. Is that smaller than the original object? No. It actually means it's 3 times taller, except what? It's upside down. This means 3 times taller, but upside down, inverted. Okay? Now then, if you got m equals 1 over 3, that means it's 1/3 the size. That means your height is 1/3, the height of the image is 1/3 the height, and that's upright because it's positive and smaller. Okay? A convex mirror, one that curves this way, will always give you an image that's upright and a little bit smaller. Classic example is when you look at somebody's, when they're wearing goggles, real reflective goggles, and you can see like a little bitty, you can see the building or something like that inside there because it's an image that's inverted and upright. All right, but anyway, now then, here, if we put the object back here, we get a real inverted and reduced object, okay, if it's beyond the radius of curvature. However, makeup mirrors are concave mirrors, all right, and here's why. If you put a makeup mirror, your face is inside the between the focal length and the mirror. Okay, so your object, you put your face here, and then what's that do? It makes it virtual, upright, and bigger. Okay, that's why makeup mirrors are concave. They're a large concave mirror, and what do we mean by virtual image? It's located behind the mirror. It's in Alice in Wonderland. Okay, it's virtual world. Okay, all right. Real means it's actually showing up in front of the mirror, which is, I've never really seen it. I've been in, Dr. Roble has tried to get me to see it. He's done stuff with mirrors. He goes, can you see that flower now? It's in front of the mirror. No, I can't. Sorry. But he goes, well, look at it with both eyes. Well, can't do that either for some reason. I don't know why. Anyway, so there's for a concave mirror. Now, these are ray diagrams. We're not. Here you go. Here is the spherical mirror equation is valid for any object position. Okay. Sign conventions for spherical mirrors are given on the next slide. Oh, I can't wait, because this is. I want you to write this. I want you to have this on your cheat sheet. Okay, when you come, so you won't get it all screwed up. Here you go. It looks hard, but it's really not that hard. For a concave mirror, F is positive. Your focal length is positive. Why? Because your radius of curvature is on the same side as the object. Okay? For a convex mirror, or a diverging mirror, the focal length is negative. Why? Because it's curving like this, and the radius of curvature is over here, while the object is over here. Anything in Never Never Land is negative. All right? Okay. DO is the object distance. Object is in front of a mirror. I won't mess with you and put, okay, say, oh, it's a virtual object in front of the mirror. The only way that can happen is if you have double lens type thing going on. I'm not going to throw those at you. I'm not going to teach this stuff to you 15 minutes on Friday, 30 minutes today, and say, okay, here you go. Master it. No, 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 no. I think you got a few homework problems you got to mess with, but that's not due for a while. All right? So, so the distance of the object, your DO will always be positive, okay? But the distance of the image, DI, now, if it winds up, is formed in front of the mirror, then it's real, and then DI is positive. If it's behind the mirror, then it's a virtual image, and DI is negative, okay? And the image orientation, M is positive or M is negative. Well, yeah, duh. Image is upright, then M is positive. If image is inverted, then M is negative. And if the magnification is less than 1, then it's a smaller image. If the magnification, of course, is greater than 1, then you got a bigger image. Okay? And your microscopes work because you put lenses in combination with mirrors and everything else, and so you can get that 400 times to 10,000 times. And if you're real adventurous, you can even take our electron microscope course where we move atoms around and stuff. You can look at atoms. All right. Some things you might want to. Okay. Be able to prove this. Kidding. Don't worry about it. Here you go. Magnification. This is where they derive the height of the object by using similar triangles, basically, is what they're doing. Because these two are similar triangles, and then something else winds up to be these two. Can't remember. Anyway, you wind up. This is another image. Find the magnification equation. All right. So that's good. Here is a good old convex mirror. Now notice, when you use the ray diagram, which is what they explain in the book, you can read about it. And the ray diagrams are actually kind of fun. If there was 25 of you and we had tables, we'd do ray diagrams. But there's 125 of you and you don't have tables, and so we're not going to go down that road. But if you want to do them, you can. I on your own sometime. It's those of you that like ray diagrams are the same ones. When you took geometry, do they still teach constructions? Like how to bisect an angle and all that kind of stuff, how to build, do they still do that in geometry class? If you enjoyed that stuff, you'd enjoy this. Same thing, okay? All right. Okay, but notice with a convex mirror, which is coming towards us here, we've got an upright. Now this image is over here, so that makes it virtual because it's with the Mad Hatter over there, all right? It's behind the mirror. Okay, aberrations. Now let's talk about lenses. Okay, biconvex is a converging lens. It's actually kind of like a concave lens, and a biconcave is a diverging lens. That type of thing. All right. I was going to give you converging lens brings incoming rays together at a focal point, and they've got a table too that I want you to write down so that you don't screw up the converging lens. This is a diverging lens, and depending on whether you're farsighted or nearsighted depends upon the kind of lens that you have. And if we had a little bit more time, which we really don't, I would talk more about that. But when we get to the human eye, which is in the next chapter, we'll talk about it some more. Okay. All right. So there's all the different kinds of lenses. I'm not going to ask you about those. You're just going to get a good old convex or concave lens type problem, okay? All right, here you go. Images formed by lenses can be found just as mirror images were found. The first two rays, in other words, you draw the first ray, you go straight in, boom, and because of the index of refraction, it goes through the focal length, like that, the one that's going parallel to this. Then you draw your second ray, which goes right through the center of, the mirror. It comes down here, boom, guess what? Looks like we're going to get an image that's, our image is going to be here. So what kind of image is that? Virtual and inverted. And it looks like it's also going to be magnified a little bit, too. Because the next ray we're going to do is going to come down through our focal length here, hit the mirror, and then go straight across like that. Yep, that's what we did. And what did you all say? Virtual. What's it say? Real. For lenses, since I can see through it, since this is a real world over here, this is a real world over here, still, too. That's a real image, okay? It's a real image. All right, so let's go. Hopefully they've got a thing here. Here we go. Here's your thing on lenses. I want you to write down and bring it for the exam. Okay? Converging lenses, also known as convex converging lenses, positive limits. F is positive. The focal length of it is positive. Diverging lens, some call negative lens. F is negative. Okay. Object distance is in front of the lens. It's a real object. DO is always positive. Okay, now here comes the tricky part. Image distance and image type. Images formed on the image side of the lens opposite to the object is a real image. That's just the way, by convention, that's just the way we do it. Okay, so for lenses, now not for mirrors. Remember, if it wound up behind the mirror, it was a negative, right? It's a negative distance. All right, but for a lens, when it winds up where it's supposed to, when the image is formed, it's a real image. And image is negative is formed on the object side of the lens, same side as the object. That's a virtual image. Because we don't really expect to see that. We're looking through a lens, and all of a sudden we're looking at an object right here. Put a lens right here. We don't expect to see, we expect to see it over here, not in front or even behind us. Okay, image orientation to magnification is still the same. All right, still works out the same. So let's do a couple of these, and then I think you'll feel confident. Thin lens equation, magnification, ta-da! It's the same. It's like the half-price store. It's the same thing. All right, except that DI, remember when it winds up on the other side, when it's a real image, it's positive. Okay, so what do the problems actually look like? What do the problems actually look like? All right, we're not going to do multi-lens things. That's ugly. But we did talk about real quick, if you've got a convex surface, R is positive, R is negative, you got it. Converging lens is F is positive. Diverging lens, F is negative. This is for the lens maker's equation, which I'm not going to get into. It's that I about assigned it, but I did want to show you this. The power of a lens may be described using diopters. Okay, and a diopter is just 1 over the focal length. So if you know the distance image, and you know the distance of the image, and you know the distance of the object, you can find the focal length. Just flip that over and put it in meters, and that's your power. Okay? And that's your power. All right. So let's take a look at a couple of these problems. Let's take a look at a couple of them. .cam. Okay. So spherical. Here we go. All right. Okay, here's the question. It says an object is placed 39 centimeters in front of a converging spherical mirror of radius of 24 centimeters. Pages 783. 783. All right. Now, here you go. It says here it's a converging spherical mirror, concave, basically. What it's saying is it's a concave mirror, and it's got a radius of curvature, R equals 24 centimeters. Have I converted that over yet? Yeah, okay. R equals 24 centimeters, and the object distance, I'm putting it back here, is at 39 centimeters. 39 centimeters. Now, if we went back to that one slide, real quick, I would know that this, where it showed the different things, well, this should be real, inverted, and reduced, and smaller when I get done. Okay? All right. What do we need to find? I want to find the image location. I want to find DI. And I want to find the magnification. What is the magnification? All right. So here we go. It's not going to be too bad. We'll do this. We'll say, first of all, what is my focal length? What's my focal length? My radius of curvature is 24 centimeters. What's my focal length? 12. Exactly. 12. Focal length is R divided by 2, which equals 12. Now, okay. Remember, now don't get confused, because 1 over F is 2 over R. I got confused on Friday. All right. So, but if I just say if I just want to find the I always start. I don't know why. I just like to start it this way. I don't like to start with inverses right off the bat. Okay. So here we go. So this shouldn't be too bad. We've got 1 over 12, then equals 1 over 39 plus 1 over DI. Okay? Now, just by looking at this, DI should wind up to be what? Should wind up to be positive, because I'm going to get 1 over 12 minus 1 over 39 equals 1 over DI. And here we go. Take 1 divided by 12. Now what I do is I just do 1 divided by 12 plus, did I hit the plus? Yes. Minus, yeah, that would even be better. Minus 1 divided by 39 equals, I got like 0.05769. I just hit the 1 over key, x to the minus 1 key, boom. And I've got 17 DI is equal to 17.33 repeating centimeters. Okay? All right, so it's di is equal to 17.33 centimeters. And now I've got to find the magnification. Magnification is equal to minus, and I always put this in parentheses because a lot of times my di might wind up being negative. And so I want to make sure I get that double negative taken care of. So I always put the magnification equation in parentheses and go, okay, minus di over do. So this would be 17.33 over 39. So we'll divide that by 39. And I get 0.44. So what is that telling me? It's a positive 0.44. Yeah, it should be negative. See, I do that so I won't get confused. It's negative. So what does this tell me? It's inverted and it's smaller. Okay? Don't let the negative sign fool you that makes it smaller. That doesn't. It just means it's inverted. Okay? All right, good. So if, like, perchance it says it's an object that's 4 centimeters high, could you find its final height? It's the image of the height image. Should be able to do that, right? Okay, and the other thing, don't forget, the magnification is equal to also the HI over HO. Notice there is no, since we're in the y-axis here, if HI is inverted, then that'll be negative, but it's HI over HO, okay, which is the height of the image divided by the height of the object. These two things are equal to each other due to a similar triangle argument, okay? Those two things are equal to each other, so you might have to use those together to figure some things out. All right, what happens? So spherical mirror equations. All right, that's a good old concave mirror. Let's look at a diverging mirror, which would be a convex mirror. All right, let's look at a convex mirror. This was a converging. This is a converging mirror, also known as concave. Now, let's look at a diverging mirror, which is convex. All right, so here we go. We're going to place an object. Going to place an object in front of this convex mirror, which looks like this. All right, right off the bat, got a convex mirror. What do we know about my focal length? Positive or negative? Negative. The focal length for a convex mirror or diverging mirror is negative. Okay? All right. So F, I know, is going to be negative when I get to it. All right? So let's just take a look at what the problem says here. An object in this case is a candle. It's placed 20 centimeters in front of a diverging mirror. So if it says it's placed 20 centimeters in front, what is that telling me? What is that from my 1 over F equals 1 over DO plus 1 over DI? Which variable is this? DO, distance of the object. All right, it says if an object is placed in front of, that's my DO. So DO equals 20 centimeters. Okay? And it says it has a focal length of negative 15 centimeters. Okay, so I don't have to think. It just told me. Negative 15 centimeters. Okay? And it says use a ray diagram, but I'm not going to do that. I want to what I want to find is the distance of the image, and the magnification. And did they give me the height? No. Oh, let's say the height is 1.2 centimeters. Okay. let's let the height be 1.2 centimeters. And yeah, we're going to have to find the height of the image. Okay? We'll have to find the height of, so there's three things. There's usually three things you need to try and find. Okay? So here we go. Pretty straightforward. You go 1 over negative 15 equals 1 over 20 plus 1 over di. And so I wind up with 1 over negative 15 minus 1 over 20 equals 1 over di. So what's di come out to be? Comes out to be a number, yeah. Oh, we can do this. We can do this. We can probably do this because this would be 4 over 60 minus 4. It's 60 over 7. I'm pretty sure, right? This is 4 over 60. This is 3 over 60. Yep. They're both negative. So that'd be 7 over 60. Flip it over. So di equals 60, negative 60 over 7. So there's my image distance. Okay. What did they tell me on that scale? Okay. So that's a oh, that's for the mirror. Gosh dang it. Oh, this is a mirror. Duh. This is a mirror. Oh, okay. Whew. I thought I was on a diverging lens. I was all discombobulated there for a second. I'm sorry. Okay, so this is a mirror. All right, so the magnification then is equal. Here's where you got to be careful with the negative. I'll try and be careful this time. Well, first of all, I got to take 60 divided by 7.
It's
Negative 8.6. Over, what was the distance of the object? 20? Aha! So I've got negative, negative here. What's negative, negative come out to be? Positive. So I got 8.6 divided by 20, which is about 0.43. So that means it's behind the mirror, it's upright, and it's smaller. Okay? So that's like when you see those reflective goggles, which are just like mirrors. You see sometimes you can always see like the buildings inside people's goggles and stuff like that. So it's upright and smaller. So the height of the image is this HO times 0.43, which makes sense to us. Multiply the original height, the object height by its magnification. That'll give you the height of the image. And so you get 0.43 times 1.2. Boom. 0.156. All right. All right. Oh, they had all the numbers right here. Okay, good. All right, good. All right. See, these aren't so bad. Piece of cake, especially compared to currents and magnetic fields and forces and stuff. I mean, this is good old fractions. That's the only thing. All right, now. Let's do a lens problem, and then let's talk about the exam real quick, or a little quiz, really. All right. Let's talk about a converging lens. All right. Let's talk about the behavior of a converging lens. All right. Which would be, if this was a marine class, I'd stomp 3 times, stomp, 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 saying know about converging lens. Okay. Because you might see this again. All right. So we don't need to talk about this part of the test when we go to the test review, because you will see a converging lens. Now, one of the things that a converging lens does is it's used in movie cameras. You might see that too. You might see it in the movie cameras. And what it does is, if you ever notice that the film going through a movie camera is what? It's upside down. But the projection is right side up. That's because your brain sees things. Did you know your brain, the image actually on your brain is upside down, and then your brain writes it for you? It tells you the world's, so actually the world is upside down. No, well, whatever. Okay, gravity is up. No, Kansas science standards again. All right, anyway, here we go. A converging lens has a focal length. All right, so this is a lens. This is a converging lens. And it has a focal length of 12 centimeters. Okay? Converging lens, and it has a focal length of 12 centimeters. And hey, here we go. It says for an object. So what we want to do is we want to find for an object 60 centimeters, 15 centimeters, 8 centimeters from the lens, where is the image formed and what are its characteristics? So they wanted us kind of do three things. Let's just take the biggest one. You all can work this. This is on page 794 if you want to work it yourself. Okay. So we're going to take this little converging lens here. We're going to mess with it some. All right. And let's say the distance of the object is now. The distance of the object is 60. 60 centimeters. Yeah, 60. All right. Now then, here we go. Yeah. All right, so we got our magnification. I'm going to write the magnification equation first because that's what I'm thinking about for some reason. I don't know why. But it also equals HI over HO. Okay? All right, equals HI over HO. Okay, and we also have our good old mirror equation, 1 over F equals 1 over DO plus 1 over DI. Well, this is a piece of cake. 1 over 12 minus 1 over 60 equals 1 over DI. Again, I got good old multiples of 60 here. 12 goes into 60 5 times, right? So I got 5 over 60 minus 1 over 60. I got 4 over 60. Oh, cool. Look, I got 4 over 60. This comes out to Fetty. Yeah, this is DI equals 15 centimeters. Okay? Hey, it's positive. It's positive. Where the heck did this thing wind up if it's positive? Yep, wound up behind the mirror like it's supposed to. Like it's supposed to. It did good. So now, I mean, it wound up behind the lens because we're dealing with lenses. So whenever DI is positive, that means it's behind the lens, okay, or it's supposed to be, all right, because the image, especially with this kind of lens, with the converging lens, we definitely want the film, which is upside down. We want it to be over to project on the screen. That would be a good thing. All right, now how tall is this thing? Is it going to be inverted? Looks like it. 15 over 12. 12, what is that all about? How about 15 over 60? There we go. So it's negative 0.25. Notice the magnification doesn't have units because this is supposed to be 60 for those of you keeping score at home. But anyway, centimeters over centimeters, they cancel. I got kind of sloppy with my units here. Okay? And so that means it's upside down and only 1/4 the size. All right? If I scoot that thing a lot closer, let's scoot it closer. Let's see what happens if we make the object. Let's go ahead and make DO equal to the distance of the object. Let's make it 4 centimeters and see what happens. I'm hoping that this will increase my magnification. Of course it will.
Is that possible?
What?
Wouldn't it disappear if it's inside the focal?
What's that?
It would disappear if it's inside the focal point on the opposite side.
Would it?
Yeah, because the light rays can't converge. Because you have to draw it going through the focal point on each side, so it would converge out here, and you can't converge to the side. So you would be able to see it.
No, it shows up. It's there. Yeah. Yeah, it's possible. What, that this isn't possible?
No, because you have your...
Are you saying this would be impossible?
Yeah, that part. Because you're...
Well, let's see what happens. I mean, I can physically put something 4 centimeters in front of anything I want.
But your focal point is 12, so you won't have an image on the other side.
Right. It might be behind me and bigger. Right.
That was like my point.
Oh, okay. I'm sorry. Okay. Duh. Right. Good. Good. Right. Might wind up behind me. So let's see what happens. Because if my DI comes out to be negative, then Cody is right. Okay. I thought she was saying, you can't do that. And I was like, I can too. 4 centimeters. There it is. All right. Now, argue with me, even though you're right. Oh, she's going to be right. Look at this. I can tell already. Because look, I got 1 over 12, which is dinky, and 1 over 4, which is a little bit bigger. I'm going to subtract. It's going to come out to be negative. So I've got 1 over, so I'm going to wind up with 1 over 12 minus 3 over 12 equals 1 over DI. And so DI comes out to be minus 2 over 6, or 2 over 12, which is 1 over 6, which is negative 6. So DI comes out to be negative 6 centimeters. Where is negative 6 centimeters if I put it at 4 centimeters? Where's negative 6? It's behind me, just like Cody said it would be. It's behind me. Very good. Good. Right. I'm not going to get an image in front. Very, very good. All right. Good. And then the magnification, let's check out the magnification. The M of this thing would be negative 6 over 4. So it's a little bit bigger. It even came out bigger to be positive 3 over 3 halves. All right, good. There we go. That's chapter 23 in a nutshell. Now, let's talk about your little quiz you're going to take. Know how please know about, and I will tell you when I pass out the quiz on Wednesday. I'll tell you, now, it's going to be a little bit tricky because remember when we were doing Snell's law, we were using degrees. We weren't using radians from chapter 22, but from chapter 21, you're going to have to use radians. All right? Chapter 21, you're going to have to use radians. So don't be afraid of this equation. The voltage equals V naught times the sine of 2 pi F times T. Okay? And what's that? Yeah, that's from chapter 21 type stuff. Okay. All right. And don't be afraid if you see a word like effective. Effective just means the same thing as RMS. There's one little part in your book that they got effective as bold, and it just means the RMS. All right. So if you're given this equation, know what the amplitude is of the voltage. Know the amplitude. Know the IRMS. And be able to figure out what the voltage is at a certain time. Not too bad. So you're given everything. All right? Those kinds of things. So you can look up some practice. There's some how to do that in the book over that part. All right? Know about your favorite RLC circuits. Okay? RLC circuits. Know how to find the resonant frequency. All right? Know how to find the resonant frequency in an RLC circuit. What's that formula? And be able to find, then be able to play with the circuit if it happens to be at resonance. Okay? Something happens when it's at resonance, okay, with your XL and your XC. Okay. All right. The lens stuff you should be fine with now. We've kind of gone over that a bunch. All right, and then last but not least, oh, there's actually 7 questions, but anyway. Last but not least, know how to, what was it? Oh, yeah. Good old, know about Snell's law. Know how to manipulate that thing. Know that the index of refraction is equal to C over V. I won't give you one with the thing being L over 10 thickness, or that is whatever that was. Know that that's the deal. And that this also means that lambda times the frequency and lambda times the frequency, don't freak out, okay? And know how to find the critical angle. Know that the critical angle of something is equal to N1 over N2. And that can only happen, though, when you're going from, well, it's actually N2 over N1. Doesn't matter. You just got to make sure you pick the one. In other words, I'm going from N1. It's got to be greater than N2, right? Otherwise, it doesn't work. Otherwise, you get the, well, actually, the sine of the critical angle is equal to that. Sine of the critical angle is equal to that. And if N2 is greater than N1, it's undefined. You can't do that. So take it from there. You'll be fine. 7 little problems, just like that. And 3 of them are just like the lens stuff we just did. So you'll just be able to crank those out. Go practice them, and you'll just crank them out. It'll be great. Yes. No short answers. Oh yeah, there's, no, that's,